So this is Jeff Hamrick at the University of San Francisco's Financial Analysis program, and I'm going to talk for a minute about running both simple and multiple linear regressions in Stata. It's actually fairly easy. I've got here our body fat percentage data set, which I've already imported into this Stata work file, so you should do that before following along with me. Feel free to pause the video. The command for running a simple linear regression is actually pretty easy. For example, if I wanted to regress body fat percentage against abdominal circumference, I just use the command regress. I put the dependent variable body fat percentage, whose name is body fat, and the one independent variable that interests me, abdomen, right here. And I get the regression output, which we had discussed in class. To execute a multiple regression, you simply take this code and add other independent variables that are of interest to you. So if I want to regress body fat percentage against not only abdominal circumference, but also, let's say, hip circumference, age, weight, and height, I get a regression output, linear regression output involving not only abdomen, but also these other independent variables as well. So let's take a minute to discuss the interpretation of that regression output, like we did in class. So if I go back and I look at the output for the simple linear regression case, here's what we've got here. 252 observations in the data set, and when we take from that sum of squares decomposition that we had worked with, the model sum of squares and divide by the total number, the total sum of squares, we get r squared, which is this quantity right here. Okay, adjusted r squared, you'll remember, is a penalized version of r squared that modifies r squared to account for the total number of independent variables in the model. Since this model has only one independent variable and two parameters being estimated, abdomen and the intercept in the regression model, the adjusted r squared is fairly close to the r squared. Okay? If you take the sum of the squared residual terms right here, and you take the average number of those in terms of degrees of freedom, that is, if you take this number and divide by 250 to get mean squared residuals, and then you take the square root of this number right here, you get root MSE. Okay? And notice that there's a certain sort of structure in this ANOVA table right here. This term plus this term equals this term plus this term equals this term, and that relationship does not hold here, but if you take this number and divide by this number, you get this number. If you take this number and divide by this number, you get this number. That's because it's, for example, the mean square for the model, which is just the sum of the squares for the model divided by the model degrees of freedom. So right here you have your table of parameter estimates. You have the ordinary least squares, fitted coefficients right here. This is the coefficient associated with abdomen. This is the coefficient associated with the constant intercept term. The standard errors of both of those coefficients are located right here, and basically this 95% confidence interval is roughly speaking obtained by doing this number plus or minus 2 times this standard error right here. And if you kind of eyeball it and do the math in your head real quick, you'll see that that's how we get the number on the left here and the number on the right here. Now, it's not actually plus or minus 2 times the standard error, but it is a t-star threshold based on the number of observations minus the total number of parameters that had to be estimated for the model, in this case 252 minus 2, or 250 degrees of freedom for a student t distribution that leaves 2.5% of the probability mass in the right-hand side of that t distribution and the left-hand side of that t distribution. So how do we get these student t-test statistics right here? If you take the coefficient and you divide by its standard error, you'll notice that this divided by this equals this, this divided by this equals this, so that's how you get those student t-test statistics. These p-values right here are obtained by using, what Stata is using is the functionality that I show in another one of my videos about how you can compute student t probabilities using Stata. But basically this is the probability that a student t variate with 250 degrees of freedom exceeds in magnitude this number right here. So as you can see, there's almost no probability mass beyond the absolute value of either 22.13 or negative 14.29 for a student t distribution with 250 degrees of freedom. So that's roughly speaking how we get these numbers right here. The one number that I have not talked about up here is this F statistic. Okay, so how do we get this F statistic? We get this F statistic by taking the ratio of the model mean sum of squares and the residual mean sum of squares. So if you take 9984 divided by 20, roughly speaking, you get 489.9. Now that is under the null hypothesis that the regression relationship does not exist. That quantity, that ratio that we just took, is a Fisher random variate with numerator degrees of freedom equal to 1. That 1 is coming from over here. And denominator degrees of freedom equal to 250. That's coming from right here. That is a Fisher random variate that lies very deep in the right tail of a very large number of Fisher distributions, but in particular it lies very far in the right tail of a Fisher distribution with 1 numerator degree of freedom and 250 denominator degrees of freedom. In fact, the probability mass to the right of 489.90 is equal to 0 up to 4 decimal places. Okay, so that means we would conclude that the regression relationship is highly significant. Abdominal circumference does indeed explain body fat percentage, and that's pretty much how we understand all of these outputs right here. If you go back to the outputs that I generated for the multiple regression model, you'll notice that everything is basically structurally the same. The parameter table is a little bit larger because we have more independent variables, but all of the same basic relationships hold that I just talked about. So that's how you use the regress command in Stata to very quickly generate multiple linear regression relationships between a dependent variable of interest and one or more independent variables of interest. Let me know if you have any questions.